So hello everyone, hope you all are doing well. So in today's video we are going to solve a blind series 33 question, which is to check if a given graph is a tree or not. So let's see the problem statement. We are given a graph with n nodes numbered from 0 to n minus 1 and m edges. We have to return 1 if a graph is a tree or return 0 if it's not. And the graph also contains self loop and multiple edges. So let's see first of all what is self loop and multiple edges is. So basically a self loop occurred when we have a edge with the same source and a destination. For example, in this graph you can see we have this edge with the source of 0 vertex and its ending at destination of the same vertex. So this means this edge has a self loop. This graph contains a self loop. And if we're talking about the multiple edges is simply there are edges. There are two or more than edges with the same source and destination. For example, if we consider this edge E1, it has a source of 0 and a destination of 1, while the other edge E2 also have a source of 0 and destination of 1. So in this case we can say there are multiple edges in the graph. So in the problem statement we need to find whether a given graph is a tree or not. So when can we say a graph is a tree or not? So we can say a graph is a tree when there is no self loop, there is no cycle, there are no multiple edges, and the graph should not be disconnected, means the graph should be connected. Or we can say basically a graph with n minus 1 edges where n is the number of vertices, which has no cycle, no self loop and no multiple edges can be called a tree. So let's see first of all what a disconnected graph is. So before understanding what is a disconnected graph is, let us understand what actually a connected graph is. So a connected graph is simply a graph where you can reach from a source to another vertex. Means is a there is always a possibility to reach from one vertex to another vertex, or you can say to all vertex either directly or indirectly. Like you can see in this graph, you can reach from 0 to any vertex, either like you can reach to 1 directly and 2 directly, and you can reach 3 also via 2 or via 1, which is indirectly. While in disconnected graph there will at least be one vertex which cannot be reached either directly or indirectly by any of the other vertices. For example, if I consider my vertex 0, so one vertex 0 I can reach to 1 and 2, but there is no path exist to reach 3 and 4. And the same if I consider my vertex 4, I can reach to vertex 3, but from 4 I can't reach to 0, 1 and 2. So in that case I will say that this graph is disconnected. And in this graph I can see there are two connected components. First of all is 0, 1, 2 and another is 3, 4. Okay, and if you consider this graph, you can see it forms a tree. As you can see, there is always a path to reach to any other vertex from either of the vertex. You can reach any of the other vertex and there is no cycle and no self loop, and also it is a connected graph. There is no disconnected component. Now how can we solve this problem? Well, to solve this problem is very simple. What we have to do is basically we have to check whether the given graph has a cycle or a self loop, or whether it is a disconnected graph, or whether there are multiple edges. If we find any of these four condition in the graph, so we can simply say this is not a tree. Or in case if we can't find any of them, so we can simply say that the given graph is a tree. And how can we do that? We can use the DFS algorithm to do this. So what actually a DFS is? In DFS we actually start from a particular node which is known as source. Then we visit it, and then after visiting that node we start visiting its neighbor. And while visiting its neighbor, at the same time we visit its neighbor and start visiting its neighbor of neighbors. And this will go on until we either we reach a dead end or we visit all the nodes. So this is basically all about the DFS, and you will understand it while we try run our pseudocode. So let's see. So in the pseudocode, here we have a DFS. Okay, DFS function which has edges, and this is the edges, all the edges that are marked in a adjacency list, and we give it a source, a parent means the parent of the current source, and the visited array which keeps the track of whether a node is visited or not. So in this function, first of all we visit the particular source that we get a node. Okay, then we start exploring its neighbor if they are not visited. Okay, and if the neighbor is not visited, so we run the DFS for the neighbor. Okay, the source neighbor, and make the make the source its parent. And the source if the neighbor is already visited, so we will check whether the neighbor is not its parent, because if I go from 1 to 2, this means 2 is a neighbor of 1. Then if I start visiting 2's neighbor, then if I reach to 1, then I can't say that 1 is a neighbor of 2, because 1 is actually a parent of 2. So because if I consider 1 as a neighbor of 2, so this will create a cycle, like I can reach from 1 to 2 and I can reach from 2 to 1. So for that reason I have to keep the track of this also, of parent also, so that it doesn't mean that there is a cycle. This doesn't create a cycle. Okay, so in this case we return true if there is a cycle, otherwise we will return false, which means that there is no cycle or a self loop. So let's consider this graph as an example, and the source is 1. So let's say we start from source 1, and there is no parent of this source because we consider this as the starting vertex. So let's say its parent is -1, which indicates that it has no parent. Okay, and we visit this node. Okay, so we visit this node. So we say we have visited one node. Okay, node 1, and now we start exploring its neighbor. So who are the neighbor of this node? Here in adjacency list we see there its neighbor are 2 and 4. Okay, so let's say we explore its neighbor 2. Okay, so we run the DFS for its neighbor. Okay, so we run the DFS for its neighbor. So when we run the DFS on its neighbor, so at that time the source will become 2 and the parent will become 1. Okay, so we visit vertex 2 also. So we visited 2 also, and now we will see who are the neighbors of this vertex 2. So its neighbors are 1 and 3. But now if we consider uh, one vertex as its neighbor, so we see that it is already been visited. Okay, if we see this condition, it is already been visited. So if we see the else statement, it say if the neighbor is already visited and it's not the parent of the source, thus 1 is a parent of this source. Okay, yeah, the source is 2 and its parent is 1. And if we try to visit its neighbor, which is actually 1, but it is its parent, so we we can't say that this is a cycle. Okay, so this doesn't mean it's a cycle, so we continue it to another neighbor. So the another neighbor is 3. So is 3 is visited, 3 is not visited, so now we will visit 3, the vertex 3. Okay, and when we visit the vertex 3, our source will become 3, vertex 3 and its parent will become 2. And now the same procedure will occur again. We will check whether who are the neighbors of this node 3. So its neighbors are 2 and 4, and you see that 2 is actually the parent of this 3, vertex 3. So this will not be considered as a cycle, and we will check for another neighbor, and we see that another neighbor is 4. So we will, and it is also unvisited. So we'll run a DFS for it. Okay, we will run a DFS for it. It is already visited, and now we will visit uh, our vertex 4. So we will mark it as visited, and this time our source will become 4 and our parent will become 3. Okay, okay, and now from 4 we will start exploring its neighbor. So from 4 we will start exploring its neighbor. So we first get 3, but 3 is actually a parent of this vertex 4, so we will not consider it as a neighbor, and it also doesn't mean that it is actually a cycle. So now if we consider another neighbor, we see that its another neighbor is 1. So we will check if this neighbor is not visited, but we see that it is actually visited in our visited array. Okay, so this neighbor is visited. So we will check our else statement. We see if a neighbor is already visited, and yes, it is already visited, and it is not the parent of the source. Thus 1 is a parent of our source, which is vertex 4. Our vertex 4 has a parent of 3, but its neighbor is 1 and it is already been visited, and it is also not a parent. So this means our graph actually contains a cycle, and in that case we will return true. Okay, so we can imply from this that our graph contains a cycle, and it means our graph is not a tree. The given graph is not a tree. As you can see, you can also see that 1, 2, 3, and 4, this graph has 4 vertex, and there are total 4 edges. And and before we said that a graph can only be a tree if there are n minus 1 edges, and there is also a cycle. As you can see, I can reach from 1 to again back by 1 via 2, 3, and 4 vertex. So this means this graph contains a cycle. So that's how we will solve a problem. But let's say if this vertex, this edge is not there, so 1 will not be a neighbor of 4. So we can say this given graph can be a tree because there will be no cycle after we visit the neighbor 3. After we visit the neighbor of the 4, which is 3, and which is actually a parent of a 4. So that's how we will solve this problem. So let's see the code. So here we are given a number of vertex, number of edges, and the adjacency list. Okay, so first of all we will create our own edges list. Okay, of uh, size n. Okay, and there are m edges, so we will run a loop to n. Okay, and I will push that in my edges list, which is adjacency list. And since it's a undirected graph, so I will also make the destination its source. Okay, and now I will create a visited array of boolean. Let's name it this. Of size depends on the number of vertex, and all the value will be false at the starting. Okay, and now I will run a DFS on it. Okay, I will give it the adjacency list. The parent will be, let's say I start from 0, its parent will be -1, and I will give it a visited array. Okay, and if it will return me true, okay, so what's the use of this DFS? It will tell me whether my this graph, the given graph, this edges, okay, is contain a cycle node. If it returns me true, this means it contains a cycle, and in that case I will simply return false, which means if my graph contains a cycle or self loop, so that means my given graph is not a tree. Okay, and for checking whether my graph is a disconnected graph or not, I will simply run a loop, okay, to check whether my all vertex is visited visit when I start visiting my all node from the zeroth index or the source. Because if I can reach from my source to all the vertex, that means my graph is actually connected. But if I can't reach from my source to any of the vertexes, that means there is at least one or more than one vertex which can't be reached from source. So in that case, my given graph will be disconnected, and also it means that my given graph is not a tree. So in that case also I will return false. If my if the visited array, if any of the value in the visited array will be equal to false, then in that case also I will return false. Okay, or otherwise I will return true. And at last, let's write our TFS function. So parent and our visited array. Okay, so first of all we will visit this particular source. Okay, so we will visit it, and now we will visit its neighbor. Okay, we'll start visiting its neighbor. We will check its neighbor in the edges list of edges. Okay, and if the neighbor is not visited, okay, if the neighbor is not visited, so we will run the DFS for its neighbor. Okay, and its parent will be this particular node. Okay, and in case if it is not visited, so I will check whether the neighbor that I am visiting, it's not its parent. In case if its parent is not equal to the neighbor, that means my graph contains a cycle. But if the neighbor is actually the parent of the node, of the current node, it means it's not a cycle. It's just an undirected edge through which I just reach to this particular node. That this particular neighbor is not equal to parent. Okay. Uh, Here also I have to check because there in future my neighbor of neighbor can also contains a cycle. So in that case also I have to check here and return false. In case if it is not equal to, here also I have to return false. Otherwise I will return true. Okay, there is a problem. We have to, in case if there is a cycle, we have to return true, not false. Okay, so let's try to run it. Okay, we are getting the right answer, so let's try to submit it. So it got submitted. Okay, so the time complexity of this code is v plus e, where v is the number of vertex and e is the number of edges, and This is the time complexity of DFS because we just apply the DFS here, okay, to check whether our graph contains a cycle or a self loop. So that's all for today. You can find the source code of this in our GitHub. The link will be provided in the description. So I will meet you on the next video.